Hi everyone. This is the first lecture in the series of lectures on RF system design. So before we start discussing the radio frequency systems, we'll spend a lecture or two on Fourier transforms and also understanding some basics of signals. So given any signal, a time domain signal x of t, uh, depending on the nature of the signal, we can either define energy or power. So these are signal definitions. We will also look at power and energy when we talk about a radio frequency system. Okay, they both are very closely related, but this is more of a mathematical convenience. The energy and power that we are going to discuss now, it's more from a mathematics point of view. Now, these definitions will help us a lot in understanding the frequency domain behavior of signals. Okay, it's a very useful thing, so we'll spend some time discussing that. Now, let's assume you have a signal x of t. Now, x of t can be a real signal or it can also be a complex signal. Then we define what we call the energy of the signal. It's an integral of x of t into x, the conjugate of t, dt. So this product of x of t with its conjugate is what we, and taking integration of it for all time, is how we define energy. Now, x and x conjugate, that's simply the magnitude of the complex number. So that's written it as mod of x of t the whole square dt. For a real signal, you won't have this modulus because x of t into x conjugate is x of t itself for a real signal. A more generalized definition will be if you have some arbitrary signal, which is if you have some arbitrary signal which is varying as a function of time, what you do is let's assume the signal goes from minus infinity to plus infinity in time. You define an interval of length t naught in time domain and compute the square integral or magnitude squared integral of this signal in that interval. So that's what I've written here. Limit of t naught tending to infinity. I'll come to that. So we'll first compute the value of this signal between minus t naught by 2 to plus t naught by 2. Squared integral of this signal. Then we let t naught tend to infinity. So in the limit, so this value, energy computed within t naught, I'll write it as E of t naught. Now, why am I defining this? It will become more clearer when we go to power of a signal. So E of t naught in the limit t naught tends to infinity will converge to the energy of a signal. Okay, so this is an energy of a signal. In fact, for what signals do we define energy? Energy is defined for those signals for which this integral converges. So this integral should be less than infinity. It should converge. It should converge to a finite value. Okay, so any signal which exists for finite interval, most of them will have a finite energy. Any signal which is confined in time domain, it is limited in time for a certain interval, will all have a finite energy. Okay, so a signal which is everlasting, a signal which exists for all time, depending on the nature of the signal, it can have a finite or an infinite energy. So for example, let's assume I have a signal of this type, e power minus at into u of t. So this is a very standard signal which you'll encounter in first order systems. Now for this signal, do you think the energy will be finite? Will the energy e power minus at into u of t, will the energy be finite? So if you draw this waveform, it's going to look like this. It's going to be an exponentially decaying waveform, e power minus at into u of t. What is energy? Energy is squared integral. So you have to square it first. E power minus at the whole square into u of t. So this will again be e power minus 2at into u of t. And you're going to integrate it from 0 to infinity dt. So this integral, you can very easily show it will just converge to 1 by 2a. So it's a finite energy signal. So the energy of the signal is finite. Okay, because it's decaying down, it's decaying down exponentially. This will have a finite energy. Now I'll just take you through some very standard pulses signals which we will encounter in most wireless or RF systems. One is the quintessential pulse signal. A signal which exists for a duration of t seconds with an amplitude a. So you can directly compute its energy, a square t. You just find the integral. You will just get a square times t. So it's proportional to the energy here is proportional to the width of the signal in time. The next signal is a sinc waveform. So here what I've shown here is a magnitude of a sinc. So sinc x, uh, the way in which we will define, I'll clearly define you. If, let's say I'm testing you in an exam, I'll very clearly define what sinc x is. But generally, sinc x definition is sine pi x upon pi x. So this is how we are going to define. I'll explicitly, let's say there is a different definition, I'll mention it clearly. So that's what I've written here. So here it is actually, I've written sine pi of t. So here the definition is sine pi of t by pi of t, sine x by x. I'll clearly write it. If I'm writing the definition, sometimes it's written as sine x by x. This is also called as sinc x. I'll mention the definition very clearly. A sinc function is actually, we will later see, it is the Fourier transform of a pulse signal, and the zeros of the sinc will be periodic. So it will have zeros at in time domain if this is your function. So the function is t sinc pi of t. So that will be sine pi of t divided by pi of t. The thing about a sine function, sine x, the zeros of the sine x occurs at n pi, multiples of n pi. So to find the zeros of this, you'll have to just equate n pi to n of t. So this is, sorry, yeah, this is not f, but rather t. It's in time domain. So I'll write pi t by t. Okay, so this will be pi t upon t. So it's a time domain signal. So it's sine pi t by pi t. So equate this to pi t upon t. So you will get t equals nt. So those are the points where you will have zeros, plus minus n pi. So you will get t equal plus minus nt. So that's the sinc function. I'll later show you how to compute the integral, because this integral may be a little bit complicated to compute. So integral sinc square this dt going from, say, minus infinity to plus infinity may be a little bit complicated to compute, but I'll just compute it in a few moments. This integral can be very easily computed using Fourier transforms. Okay, so sinc function has a tendency to decay down. If you compute the peaks, it is a sine function, but the amplitude of the sine function keeps decaying as time increases. Okay, so amplitude will go down linearly. The amplitude will decay down, okay, hyperbolically, 1 by n. So for the first cycle, if it is 1, it will be 1 by 2, and so on. It will keep decreasing. The peak value will keep decreasing. So it's, what is a sinc function? You just take a sinusoid. In fact, you can easily construct a sinc function. All you need is just take a sinusoid, multiply it with 1 by t, multiply it with a function which looks like this, 1 by t. Okay, so multiply it by 1 by t on either sides. You will get 1 by t is a function which tends to 0 t equal to infinity or minus t equal to, say I'm plotting mod of t. Okay, so what happens is for negative values of t, so for negative values of t, sine t by pi t, so it will actually be an even function. So that's why I'm using mod of t. So you'll have to multiply a sinusoid by this. So that's why you get a function that will look like this, a decaying sinusoid whose amplitude will decay down as 1 over t. Okay, so that's a sinc function. We'll try to see how to compute the energy for it in a very simple way. It's easy to do that. The next and another important signal is a Gaussian signal. So this, why am I discussing these signals, is that these are the signals which we will be using. For example, Bluetooth uses a modulation scheme called GFSK, Gaussian frequency shift keying. And the pulse shapes in time domain look like a Gaussian function. So that's why I'm talking about the Gaussian function here. A Gaussian function will be of this type. It will be of this type, e power minus t square times some constant. It will be of this type. It will decay down on either sides as t tends to infinity, plus or minus infinity, it will decay down to 0. And the width of the skirt of this Gaussian function is determined by a variable called variance. I think most of you would have taken any basic introductory course on probability and statistics, will be aware of the standard Gaussian function. So I'll write the standard Gaussian function in this way. So root of 2 pi sigma square e power minus 2 t square by 2 sigma square. So this is what we call a zero mean Gaussian function. So this function is it an even or odd function? What kind of a function is this? Is it an even or an odd function? So it's an even function. So for an even function, f of t should be equal to f of minus t. We'll have to satisfy this condition. So this here is an even function. So which means it's going to be symmetric around y-axis. So it's going to be whatever waveform is on the x side, it's going to look exactly symmetric on the minus x, the negative x-axis as well. So that's a Gaussian function. And how much is this function going to spread? That information is contained in this variable sigma. You can see here itself, if you increase sigma for a larger value of sigma, if your sigma is very large, e power minus 2 sigma square, if your sigma increases, e power that value decreases. Because e power, a very small value, if your sigma is very large, you get e power a smaller quantity. Okay, so then that function the Gaussian function will become flatter and flatter. So if you keep increasing sigma, the Gaussian function is going to look like this. Okay, so if I keep increasing sigma, I'm trying to draw this function here, guys. This is the function I'm trying to draw. What is the area of this integral? What is the area of this integral?
So
1.
1. It's a standard probability density function. So integrate this, you will get 1. Okay, so maybe it's an open book, so you can just remember this result. You use this equation. With this you can do a lot more analysis. So since this area is integral is 1, if I increase sigma, what is going to happen is this function is going to spread, but the amplitude is going to decrease. So what will happen is the function will do something like this. It will spread more and it will flatten out. Okay, I'm not sure if the color is visible. So yeah, it will spread more and it will flatten. The function will flatten out. Why will it flatten out? Because the area is 1. The area here is independent of sigma. If you see here, this area is independent of sigma. So which means the area under the green curve should be same as the area under the yellow curve. Now, as I decrease sigma, if I decrease sigma, what will happen is if I make sigma smaller and smaller, the function will become more narrower because your sigma is smaller and it will peak like this. Okay, so this is smaller sigma and it will peak, the function will peak. Eventually, if sigma tends to infinity or 0, what do you think will happen to this function? The function will shrink. The function will shrink to smaller and smaller and smaller and smaller values. But remember, the area is independent of sigma. It's always 1. The area is always 1. It will approach an impulse function or a delta function, Dirac delta function. Okay, it will approach an impulse function. A Gaussian function with negligibly small variance will eventually approach a Gaussian, an impulse function. So that's it. Now, how to compute the energy of the signal? So again, this is a useful signal to remember. So what I have considered is, I have considered a Gaussian pulse of this type. The pulse looks like this: e power minus t square by 2 sigma square. This is your Gaussian pulse. I have not multiplied it by 1 by 2 pi sigma square. I have not done that. That's just a probability density function. Now your job is to find out the energy of the signal. So how do we find the energy? So integrate this function and square it. If you square it, you will get a factor 2 here, dt, going from minus infinity to plus infinity. 2 and 2 will cancel out. You will be left with an integral which looks like this. So you will have integral minus infinity to plus infinity e power minus t square by sigma square dt. Now you have to evaluate this integral. How do you do that? Compare it with this. You know this result. Using this result, If you should be able, if you can write this expression in terms of this, then you're done with it. So first step, you need to find what is the variance. So here the variance is not sigma square because there is no 2 factor here. So I'll multiply it by 2 and divide by root 2. So I'll write the variance of the new function is sigma by root 2. So multiply by 2, sigma by root 2 the whole square, you will get the same function here. Okay. Then now if I know the variance is sigma by root 2, I'll just multiply and divide this function by root of 2 pi sigma dash square divided by root of 2 pi sigma dash square. Now the value of this integral is 1. With when you multiply it by 1 by root of 2 pi sigma square, you get 1. So the answer will be root of the value of this energy is going to be root of 2 pi sigma dash square. Now sigma dash is sigma by root 2. So you substitute it, you will simply get root of pi into sigma. So this is an energy of a Gaussian pulse. Remember that I have very clearly defined the Gaussian pulse this way. E power minus t square upon 2 sigma square. This is my definition of a Gaussian pulse. I can always multiply it with some constant factor a. In that case, what will be the energy? What will be the energy if I multiply it by a? You just have to multiply this result by a square. That's it. So you will get a constant a square factor everywhere. We'll have to simply multiply this by a square. Okay. So if I want to increase the energy of the Gaussian pulse, there are 2 ways in which I can increase. I can simply just scale the Gaussian pulse, increase its amplitude, or I can also increase its variance. I can just increase its sigma. We'll see what is the effect if I increase the variance once we talk about Fourier transforms. Okay, so I've taken, so far what I've discussed what definition of energy of a signal. Then I took some standard 2 to 3 signals, a pulse, a Gaussian function, and also we have taken a Sinc function. I haven't computed its energy, but I've just introduced you to a function that looks like a Sinc function. Why did I discuss Sinc functions? Because when we talk about transmitting signals, so there is an interesting signal called raised cosine filter, which is derived from, it looks like a Sinc, but a modified version of a Sinc. Sinc rolls off with a slope of 1 by f. Raised cosine pulses will have a rolling factor of 1 by f square. Okay, they will roll off faster. So that's why I discussed that function. The other function we discussed was a Gaussian function. And we saw how to compute energy of a Gaussian function. Okay, I told you it's better to remember one integral. With the knowledge of this integral, you can solve the energy of a Gaussian very easily. The next pulse is a finite duration sinusoid. A sinusoid that lasts for one time interval of t seconds. What is the energy? What is the energy of this? So this is a sine omega naught t, and the function x of t equals a sine omega naught t for t varying from 0 to t. It is 0 elsewhere. Okay, for t not in this range, elsewhere this function is 0. Okay, so that's simply a truncated sine wave. You took a sine wave, truncated it for one cycle, and we can define energy for it. So generally I said energy will be finite for signals which are of finite duration. So the energy of this signal is simply given by, just have to square it, and you can easily show it will be a square by 2 into t. See, I'm not going through this integral. It's a very trivial integral. So you will get a square by 2 into t. So that's the energy of a single pulse sinusoid. Compare this with a pulse. I had a pulse whose width was t seconds, amplitude a, that was a square t, right? That was a square t, but this is half of that energy. Now, can you tell me what will be the energy of this function? So I have a pulse which goes from 0 t by 2 t seconds. It is plus a for half a cycle, minus a for half a cycle. So what is the energy of this signal?
A square t itself.
A square t. It's same as the pulse signal. Okay. So if you take a sinusoid here and try to fill this with a sinusoid, you can see that a sinusoid, it's not fully filling it, right? So it's of course square. It's going to integrate more because its value is constant for a longer duration. Okay, so that's why you lose that half factor. For a sine wave, it only integrates to half of what a pulse signal will do. Okay, so if you see here, energy is not a unique number. I can have different signals having same energies. Okay, energy is not a unique number. It's one of the characteristics by which you can define a signal. Okay, it's one of the defining characteristics. Sorry, but it's not a unique characteristic. It's one of the ways in which you can characterize a signal, but it's not a unique property. Multiple signals can have same energy. So, for example, so I can have these two signals will have same energy. I can define a signal this way. Okay, all these signals, they will all have same energies. Next, we'll talk about power. So power is defined for those signals which are everlasting, which for which energy doesn't converge. Okay, so this is also another important characteristic for a signal in which we characterize by which we can characterize a signal. So how do we compute power? First, compute the energy of the signal, define an interval t naught. This t naught has nothing to do with the signal, it's just an arbitrary variable. Define a time interval of duration t naught seconds. Let's assume the signal is going from minus infinity to plus infinity. So then around 0, define an interval of minus t naught by 2 to plus t naught by 2. And then calculate its squared integral. So the same way, I'm going to compute this here. If you see this integral here, integral minus t naught by 2 to plus t naught by 2, x of t into x star of t, x conjugate of t dt. This is nothing but energy computed in an interval t of t naught. In case of power, what you do is, it's actually power by the definition is rate of doing work. So you find this energy and compute its average. So divide it by the time interval for which you are integrating it. Okay, divided by the time interval for which you are integrating. Then what you get here is P of T naught. In the limit T naught tends to infinity, this number will approach the power of a signal. So it's compute the energy integral and let T naught tend to infinity and then divide it by T naught. And then let T naught tend to infinity, then you will get, if the number turns out to be finite, then you can say that's a power signal. Now look at this expression. As T naught tends to infinity, if you want this to be finite, this term E of T naught by T naught to be finite, what should be the nature of E of T naught? What kind of proportionality? Should it depend upon T naught? Of course, it's going to depend on T naught. What kind of dependence should it be? Remember, I want it to be a constant. Let's say I want it to be a constant. Then what kind of dependence should E naught have? E of T naught have?
Multiple of T naught.
Multiple of T naught. So, or yeah, some proportional to T naught. So if E of T naught is proportional to T naught, then the ratio of E of T naught by T naught will be a constant. So that's it. So most power signals are those power signals whose energy will keep increasing as you increase the interval of integration. Okay, so if E of T naught is proportional to T naught, what is the energy of the signal? As T naught tends to infinity, the energy will also become infinity. But look at it, if you plot T naught versus energy as a function of T naught, if it increases linearly with T naught, then the power will be finite. The power will be finite and the signal will be called as a power signal. Okay, for signals which are power signals, energy will be zero. Energy will be infinity. Sorry, energy will be infinity. For an energy signal where the energy is finite, what will be the power? E of T naught is independent of it, it's finite. Energy will be finite, then power will be zero because you're dividing it by T naught. If T naught is very large, then the power goes to zero. So for energy signals, power will be zero, and for power signals, energy will be infinity. And the interesting fact is that for power signals, your energy will increase linearly with the interval of integration. It has to. If it doesn't increase linearly, for example, if E of T naught is proportional to T naught square, square of the integral into interval of integration, then what will happen to its power? Power will become infinity, right? You will get t naught square by some constant times t naught square by t naught. As t naught tends to infinity, your power will tend to infinity. So in that case, such signals will be neither energy signals nor power signals. Okay, so that's a very important thing to remember. Your energy should increase linearly as you increase the interval of integration. So we'll take some pretty standard signals. One, this signal, it's one of the most commonly seen signals. It's the DC signal. It is constant for all time. Okay, the output your battery chargers will give you, it's a constant DC signal with which we'll charge our phones and laptops. It's a constant DC signal. Now, if I define an interval of integration, say minus t naught by 2 to plus t naught by 2, and compute its energy in this interval, what am I going to get? I am going to get a square into t naught. If you integrate this in this interval, you will simply get a square into t naught. So now you can immediately see its energy as is proportional to the interval of integration. So which means if I divide it by t naught, if I take e of t naught, a square t naught by t naught, then this number will become a constant. Okay, so this term is what we call the power of a signal. Okay, so for a DC signal of amplitude A, the power is a square, square of the amplitude. So here it's independent of time. You can see that it's independent of time. Okay, time variable, whereas energy had some units of seconds. T was present there. Okay, remember guys, this definition of power is what I'm defining it for a general, from a signals point of view. Very soon, probably in the next week's lectures, we will start defining power slightly differently when we talk about RF circuits. We'll introduce a resistor and all of that. Right now, we don't care about, it's just a very signal processing definition of uh, energies and say energy and power. It's very useful when we interpret Fourier transforms. And also the initial discussions of amplitude and frequency modulation, I'll be using all these definitions, which is why I thought I'll spend some time to talk about this. Now let's talk about a step function. A step function which starts at 0 and then goes to infinity, and it is 0 for negative values of t. Now what do you think will be the energy? Energy for an interval of t naught by 2. Let's say I define t naught by 2 and try to compute this integral. What will be E of t naught? A square t naught by 2, right? It's finite only for t naught by 2. Here it is 0. So it will only be half of what you got for a constant DC signal. So it will be a square t naught by 2 and divided by t naught. You divide this by t naught, you will get a square by 2. So that will be your power of a step function. Step function of an amplitude A. So the signal is A into u of t. Energy is infinity. If you compute its energy, it's going to be infinity. But power will be equal to a square by 2. It's finite. It's only half of it, right? Because the signal, if you compare it with the DC signal, it exists for all time. But this signal step function exists only for positive values of t, which is half of the time of existence for a compared to a DC signal. Therefore, its power will also be half. Okay, the power is a square by 2. Next, another more important signal, which is a sinusoid, a cos omega naught t or a sin omega naught t. These are again everlasting signals. They are periodic signals. They repeat periodically. They can exist from minus to plus infinity. Just few moments ago, we computed the energy of a signal which was lasting for t seconds. We computed the energy of a signal which was lasting only for t seconds. And if you recall that result, what was that? What was the energy in t seconds? A square t by 2. Right? It was a square t by 2 if I compute the energy in t seconds. Now let's define t naught as a multiple of t. I'm going to define t naught as a multiple of t, nt. I'm going to define it as nt. So if I compute this integral a square sine square omega naught t dt for nt seconds, where nt is here is t naught. then I'll get this integral as a square by 2 into nt, right? It's n times you're computing the same integral. So it will be n square, a square by 2 into nt. Divided by nt, you get the power. So the power of a sinusoid is a square by 2. It doesn't matter whether it's cosine or sine, the power is a square by 2. Okay? So for a sinusoid, the power is a square by 2. I'll now just define one very important property, which is very useful. I know that most of you would have already studied this in your undergraduate courses. It is property of orthogonality. If you have two signals and you compute this integral x1, x2, x1, x2 conjugate dt, then if this integral is 0, then we say the two signals are orthogonal. This integral is also defined as the inner product of two signals. It's very much like dot product of two vectors. If the dot product of two vectors are 0, we say that the two vectors are orthogonal, which means you cannot represent one signal as a function of the other signal. Okay? Or also I can use the standard terms from vector algebra. I can say you cannot project one vector onto other if the two vectors are orthogonal. So the same way, I can say I cannot project x1 on x2. They are like vectors which are orthogonal. If this integral is 0, then I'm going to call x1 and x2 as orthogonal signals. If x1 and x2 are orthogonal signals, let's say we define a third signal y of t, which is the sum of some scaled sum of x1 and x2, and you're interested in finding out the power or energy of y of t, the sum of these two signals, you can very easily show. You can just, if you integrate this, square it and then integrate it, you will get a square plus b square plus there is a product term 2x1 x2. Since that integral is 0, this integral is 0, the power of the total signal y will simply be the sum of the two individual powers. It's a very useful property. So if you have n orthogonal signals, x1, x2, x3, xn, and all of them are orthogonal, then you can simply, if you're asked to find the total power of the transmitted signal, which is sum of n orthogonal signals, that will simply be the sum of the individual sig powers. So it will be p1 plus p2 till pn. Okay, so if that's a very useful property, follows from orthogonality. If you define a function of this type, say a1x1 plus a2x2 plus till a(n)xn, this is your signal. Then if you're asked to find the power, what will be the power? Because the only difference is I've multiplied it by a1, so it will be a1 square p1 plus a2 square p2 and so on till an square pn. Okay, so your powers will add up, an square pn. So if you have n orthogonal signals which obey this integral, when I say orthogonal, they obey this integral, this condition where the integral or the inner product of the two signals is 0. Okay, so then we define such signals, we say that those two signals are orthogonal. Therefore, the powers can be, if let's say we sum those such two signals, then the total power will simply be the sum of the individual powers. It's a very useful result. Now we can use that, but we can also compute some other important function. This function, a e power j omega naught t, is what we call a complex exponential. A complex exponential, it's a sinusoid, but not a complex sinusoid. You can call it as a complex sinusoid. You can use Euler's expansion. If let's say we have to use the Euler's expansion, we'll get a cos omega naught t plus j a sin omega naught t. You can immediately see cos omega naught t and sin omega naught t are orthogonal to each other. You just compute this integral over a long time interval, cos into sine, you will get sine 2 omega naught, and you integrate a sinusoid for a long time, the area under a sinusoid will be 0. The average value of a sinusoid is 0. So the area under that curve will be 0. So you can instantly see they both are orthogonal. So if you're asked to calculate the total power of this signal, what will be that value? the individual powers, sum of the individual powers of these two signals, plus here the complex coefficient is j, the magnitude of j is 1. Okay, I should probably write it this way. Um, yeah, so let me use a different page. So let's say we have y is a1 x1 plus a2 x2 and so on till an xn. So this is n signals orthogonal. I've added them with some scaled factors. Then the power of the signal y is given by mod of a1 square. So previously when I wrote that was real, a1 they were all real values. If they are complex numbers, then it's again it's not difficult to show. You can easily show this result. Mod of a2 square p2 plus mod of an square pn. The power of your total signal will be a linear sum of individual powers multiplied by the scaling factor. Okay, squared or magnitude of the scale, squared magnitude of the scaling factor. So using that, we can directly write, if you have a complex sinusoid, a e power j omega naught t, this is going to be a cos omega naught t plus j a sine omega naught t. So the power of this signal is going to be the power of cosinusoid with an amplitude a, that's going to be a square by 2 plus mod of j the whole square into a square by 2. So that's the power. A sine omega naught t is a square by 2 plus into mod of j the whole square. So you will get a square. So that's the power of a complex exponential. It's a complex signal. Okay, it's a complex signal, and the power of a complex signal is, okay, it's twice compared. A complex sinusoid is twice compared to its real sinusoid with the same amplitude. In fact, you don't have to use that. I mean, you can use the direct result itself, the direct standard way. Take x of t, mod of x of t the whole square dt, and if you compute the power, it will immediately reach, you will immediately get a square. Immediately you will get a square. Now, I'll also show you in the same way, you can define power for a cosine as well. A cos omega naught t. A cos omega naught t can be expressed in terms of complex exponentials. A cos omega naught t can be written as a e power j omega naught t plus e power minus j omega naught t by 2. So it is sum of two complex exponentials. Again, you can easily show e power plus j omega naught t and e power minus j omega naught t. They both are orthogonal. Okay, they both are orthogonal because you cannot express one as a scaled factor of the other signal. So again, these both are orthogonal signals. The moment you know these both are orthogonal, you know what is the power of a signal e power j omega naught t. What is the power of a signal e power j omega naught t? Just e power j omega naught t 1. Is that fine? The power of a signal e power j omega naught t is just 1. If that is 1, how will you calculate the power? These two are, these two signals are orthogonal. So the power is given by a square by 2, a by 2 the whole square. So both are multiplied by a by 2, a by 2. So it will be a by 2 whole square plus a by 2 the whole square. So you'll get a square by 4 plus a square by 4. So the total power will be a square by 2. That's the other way of showing it. You can easily show it for a sinusoid as well, a sine omega naught t as well. Okay, so that's it. I have discussed about the definitions of energy and power for some standard signals that we'll encounter. In the next lecture, we'll start with Fourier transforms, and I'll start afresh in the next lecture itself.